El profesor Nessim Sibony, lo invitamos, va a estar aquí unos días, ¿sí? Y aprovechamos para que nos dé una conferencia. ¿Sí? Él es de la Universidad de París del Sur, de Orsay, ¿sí? Y es un experto en sistemas dinámicos, ¿sí? Y ahora nos va a dar una conferencia sobre ergodicidad única para foliaciones en CP2 con curva invariante. ¿Sí? Muchas gracias, profesor.
Thank you very much. Really happy to speak here, and but I want just to ask you a favor, since we are just between us. If I say something that's not clear, please just interrupt. Especially that though the subject is familiar to people here, like foliations, there are different points of view, and apparently people using currents have not been so successful for the time being in convincing the others that they should pay attention. So there is a theorem, difficult, that I proved with Dean recently, but I'm going to start differently. Take a compact space X and a continuous map F. And you want to study the statistical behavior of orbits because the behavior of its individual point is far too difficult. Then, without any doubt, one of the main theorems of 20th century is Birkhoff-Ergodic theorem. What he says this: you have first to look at probability measures which are invariant. Okay? That means for any test function. The second point is that it's easier to consider only the ergodic ones, which means you cannot decompose mu into two invariant measures. Then you put Dirac masses at the orbit. Fix is the image of x under the iterate. And then Birkhoff says these converge to mu almost everywhere. This means if you see things only with respect to mu, basically you converge to the average of mu, which I can write a little differently. Average in time is equal to average in space. And this has a very long history, and that's at the basics of ergodic theorems, probability, etc., because you want to understand the statistical behavior of things. And that's it. Let me give an example which is the simplest you can imagine. It's just irrational rotation of the circle. So the orbits are dense, and it turned out in that case even invariant measure is unique. It's just the Lebesgue measure on the circle. But most of the time when you take other dynamical system, there are plenty of invariant measures, and you have to distinguish them using other functionals like entropy or things like that, and they describe to you your dynamical system. Let me point out here a very important point here is that the time is clear for us. The time is this number n. This is a time n. So the time is just discrete. Okay? And we have this important theorem. Let's now turn to a more delicate dynamical system. I'm in C2. This is a differential equation. You can look at it in real time or in complex time. I'm going to look at it in complex time. And then you can see the solutions as immersed Riemann surfaces. Horrible Riemann surfaces. They don't correspond to our intuition of a Riemann surface, which we see as a torus where we have something nice compact. Because you should see these Riemann surfaces rather as dense. So really difficult creatures. And then it's nice to extend the foliation to P2. Here you take advantage that the P and Q are polynomials, and you see it rather as a foliation in P2. Since I'm going to come back what is the meaning of foliating in P2 precisely, but since I'm going to speak on generic, I want maybe to introduce the space of foliation of degree D. If we are in pk, then I look in ck plus 1 at vector field and fg now are homogeneous polynomials of degree D. And these guys, since they are homogeneous, the orbit descend nicely to the projective space. So I will put on the space of foliation, which I identify with this vector field, the topology of these guys. And you discover immediately something important, that all these foliations have singular points. Okay? That means when you look at it in coordinate chart like here, there are points where P and Q vanish simultaneously. That's a singular point. And it's control a lot of what's going to happen. When you open a book on foliations, at some point you don't understand what's going on, because the book in general is about foliations without singularities. So you avoid the main example. Most of the theorems you look at are for foliations without singularities. So, let me come back on the meaning of foliation, mostly in dimension, whatever, 2. It means you have an atlas, and the change of coordinates is this one. That means like for any differential equation, locally, you have just parallel disks, holomorphic disks, and T is the transversal. And when I follow one solution, this picture is very, very misleading. Here I'm far away from a singularity. I can come back here. So indeed, this guy and the guy below are in the same leaf. They are not independent as it looks when I just draw the picture like that. And at a singular point, I look at the vector field and I write the eigenvalues of the linearization, and the singularity is hyperbolic, is lambda I, lambda j, not in R for all choice of A, I, j. So this is again a generic condition. It's obvious because real is too small, then you just push and you are complete. I don't have time, but I encourage if any student is here to analyze the solution of this when lambda is in C. This is a very easy case because you can write explicitly the solutions. And the solutions is WE to the lambda zeta, no, Z, and Z is E to the zeta, and I put a constant. Yeah. And when lambda is not real, you turn around the separatrices, and this is going to play a role later. So here I have kept Birkhoff theorem. What do we want? We want to understand the global behavior of leaves. How do they distribute? It's not clear what's going to replace invariant measure, or even what's going to replace fixed point. The first idea that comes to mind is that fixed point should be an algebraic leaf, like in this example, line at infinity. And then we are going to look, according to Poincaré, to what happened on a transversal. It turns out that there is a theorem by Joanolu which says, generically, there are no algebraic leaves. So, we cannot stop. The other idea that comes to mind is the following. Okay, we have this picture, and we have a transversal here. Then what happens when we slide along the leaves? We must guess an interesting object. That is, we want to look at an object V alpha is this. And we want to construct a measure here on the transversal so that when you slide till here, you get the same measure. So, since people are not too clear here with differential geometry or currents, I want to consider this object as a phi is a test form by degree 1, 1. And this means supported in B. This means the current of integration of phi d mu alpha. This is the mean. But this is local. I have said something in a flow box. That's no interest. I want something global. Okay? And then it turns out that it means if this guy were to exist in a coherent way, it means that the current T would be closed. Okay? If this is an observation due to Sullivan. If this guy were to exist, the current would be closed. Because the point here is that you have duality formulas if you want to. So you can define what is a closed current when it exists. Okay? So we would have been very happy if there is an object which looks like this, but globally it's closed. This is meaning that mu will be invariant under sliding. That means we would like to have an object, P, so that when you wedge with any form which determines the foliation, it's 0, T is positive, and T closed. Then life would be simple. Unfortunately, these guys don't exist. Generically, they don't exist. Because the dynamics would be too simple. It would mean that when you travel from a place here to a place here, you are transporting a measure invariantly, and it means that the leaves won't separate too abruptly. Okay? It turns out that instead of this, we are going to ask this. And yeah, it would mean that T is like that, but H alpha is harmonic positive. Okay? It's harmonic positive, and then these guys do exist. In the non-singular case, in the classical foliation theory, it was a theorem by Lucy Garnett, but in the singular case, it's an observation by Bo Bernson and me. Let me try to give you a hint of what it means, another way somehow to construct this current, and to express some statistical properties. It's, in some sense, you know, it's step 0. Before proving ergodic theorem, you need to introduce invariant measure. Okay? So here, before proving ergodic theorem, we want to have a way to measure. Okay? So let me give another hint. In this black book here, a good way to construct invariant measure is just to say, since these guys are measures, some cluster points are invariant measures. That's a cheap theorem. It's just use compacity of probability measure. So it's easy to construct an invariant measure by averaging on an orbit. Okay? The depth of Birkhoff theorem is that it doesn't say you extract a subsequence. It tells you the average which converges. Okay? So let's do that here and see whether it's possible to construct invariant curves. Assume for simplicity that I have a foliation in P2 with singularities. Anyway, they are always singularities. And the degree of the foliation is D. This is why I defined it. And I assume that all the singularities are hyperbolic. Then there is a nice theorem by Linz-Netto, and it has a long history, Blutzuk, others maybe. They say that under these assumptions, the Riemann surfaces, which are the leaves, are hyperbolic. It means that you have a universal covering map to the leaf from the unities. It's not C, it is a universal covering map from the unit disk to. But you know, if you it's quite difficult to work with universal covering maps. Even the universal covering map for C minus 2 point is very difficult. Okay, let's take that for granted, and let me construct the current. I am going to mimic this average. I consider the following current, tau r, it's very mysterious what I'm writing, because, and Tr is the Nevalina characteristic function. I have P2. I have a Kähler form, omega. This is classical in one complex variable. This is the Nevalina characteristic function because it tells you what is the area of the image, okay, counted with multiplicity. So it describes the growth of phi. Okay? What is the meaning? And then I'm going to divide by 1 over Tr here, so that this current has mass. So let me tell you what is tau r. Tau r is a current, and I have to describe how it acts on a test form. Like when you describe a distribution, you have to say how it acts on a test function. here is the formula. I'm just integrating, this is the leaf. I stop at time r, at hyperbolic time r, and I integrate like that here. But since if I do that, I'm going to converge to infinity, then I divide by the mass to have bounded parts. Like here, I divide it by n. Here, the time is hyperbolic. I have to divide by this quantity, which I didn't invent. It comes from Nevalina theory. Then the claim is that any sequence converging, any limit, is going to satisfy all these conditions. Which means any limit in a flow box away from the singularities is going to be defined this way. So it gives you this action, this very nice action. Oh, I have skipped one difficulty. One difficulty, it is that to make sense out of this, you need that this tau r goes to infinity when r goes to 1. That means that the total mass goes to infinity. And that's a dynamical theorem due to Fornes and myself, because you have to analyze how much hyperbolic time you spend near the singularity and get some estimates on the area. Okay? So here, even to introduce it from this point of view, you have, there is a reasonable amount of difficulty already with the definition, but once you have it, you have it. Okay? Okay. Are there any questions? No, it works in any compact Hermitian manifold. You don't need K. You don't need K. It's just Hermitian compact manifold. This theorem also works always. The singularities have just to be isolated. What? What? No. Has nothing to do with hyperbolic. Nothing. Just isolated is enough. Hyperbolic is used to say that this map exists. That the universal covering map of the leaf is where hyperbolic is. It will be used later because it's crucial. And the theorems I'm going to speak about are valid only for hyperbolic. But it's fine because it's a generic situation. And otherwise, they are open. You can try to work out other examples that would be very interesting. But I can tell you one of the difficulties, it did not appear for the moment, is when I'm in hyperbolic singularities, I have this local situation where I can describe things completely. And it is very, very useful. I would be very happy if one of you guys solve the following problem. Take a singularity which is not linearizable and help me writing some estimates for the local solution, just local solution. It's difficult, it seems to me. For example, there are estimates of the Poincaré metric near there. I don't know. It's doable, but you have to work, you know. You have at least to be a good student. So it's difficult. You have to come estimates of Poincaré metric, and then that's difficult. So this is why I choose hypothesis. Besides, sometimes in the theorems, it's used in a crucial way. Yeah, I should tell you one thing, that it turns out that in this situation, this has this growth. It has this growth, and basically, generically, but that's the other, it's very difficult. You prove it has its equivalent to that more or less most of the time, most of it. But that's very delicate because, as I told you, it's difficult to compute with universal covering map changing from these to these, etc. If some of you did hear of Nevalina theory, actually Nevalina considered in his theory not only maps from C, but maps from unit disk to C or to P1. It turns out that he had this condition, but his theory works if you don't have this estimate. That means if the quotient goes to infinity instead of being bounded. That's a funny point. So let me state just for background, because this is not what I'm being concerned today, for Ness and myself. F foliation in CP2, hyperbolic singularities, no invariant curve, this is generic, then there exists a unique directed DD bar closed current of mass 1. And this is a unique ergodicity theorem because it says that tau R phi converges to T. So it tells you that these guys I have written here, that these guys always converge to T theta. like for an irrational rotation. So it tells you very precisely, it's not almost everywhere, it's everywhere. It's everywhere. It tells you, you have this lift, then you do some averaging here, and you end up with the limit given by t theta. And it's unique. It's not even clear the limit should exist. And this is a theorem for CP2. So now let me turn to the title of my talk. Actually, I have other results, but I better skip them. I better skip them. See, I need an eraser. Now, I'm going to speak on a class of foliations where at least several people here have worked on. It is somehow the class considered by the Russian school. You can be Mexican and still be in the Russian school. So we look at foliations in C2 . P and Q are polynomials of degree D. In an affine chart. So this is not invariant when you change chart. This is why the notion of genericity is not the same. But let's consider we are here and the line of infinity is invariant when you extend the foliation to P. So we are not, in the case of this theorem, no invariant curve. Then people have, this is the line at infinity, and generically you have d plus 1 singular point on L infinity. Another generic assumption, I can assume all the singularities are hyperbolic. And I can assume also, but this is not really necessary for me, that no other invariant algebraic curve except for the line at infinity. And then there is a theorem by Huda Veronov, which I like very much. The theorem says for generic F, all leaves except for the line at infinity are dense. That's weird, you see, because you have these nice solutions of differential equation, and you should see them as just dense guys. So how are you going to predict the behavior of these guys? Okay? So the interesting point for me was, well, this current, this line at infinity is a positive closed current, directed by the foliation F. So, yeah, exactly. But do the other solution, how do they distribute? They distribute according to which law? Birkhoff's theorem is the law of large numbers. So since Khudai-Veronov says leaves are dense, there must be T positive supported everywhere, and the leap should spend as much hyperbolic time near the line at infinity and elsewhere. Somehow, what do I mean by this? Because the current I'm considering is what? Is 1 over TR You see, I integrate over the image, do some averaging that comes from Nevalina theory, and look at the limits. So what are these limits going to be? This is my problem. And it depends on R, and in principle, there are good candidates to be DD bar closed current, giving the laws of our dynamical system, which is just a differential equation. So the theorem we proved last year, Dean and me, was a surprise to us because for quite a while we tried to prove the contrary. The previous hypothesis, singularities are hyperbolic. The only DD bar closed current directed by the foliation of mass 1 to be non-zero somehow is the current of integration on the line at infinity, which means that the current tau r, which makes sense even when they are algebraic curves, converge to the line, the current of integration. So the statistical behavior is very weird, though the Riemann surfaces are dense, but most of the hyperbolic time they spend is near the line at infinity. This is what it says. It is surprising for another reason. In general, in dynamics, you expect that the equilibrium measures are non-singular. Here we have the maximum singularity. It's like if you prove, and actually it exists, but it's a curiosity if you take x squared plus c in the real line, and apparently for some values of c you have generic averages a la Birkhoff converged to a Dirac mass. Okay. Here, this is the generic situation. What's good for this, the theorem with poorness is really a theorem in CP2 because the method is just by brute force. The theorem prime is this. M omega compact Kähler surface, Kähler is used. F foliation with only hyperbolic singularity. E is the span in H11 MR of the cohomology class of curves tangent to the foliation. There is a hypothesis, but maybe just let me assume that omega is in E, that the Kähler class is in E. But I can do much weaker than that, but for simplicity. Then every dD bar closed current directed by defoliation is a linear combination of current of integration on Ci, on the curves. There is no diffuse part. Okay, so the invariant curves, compact algebraic curves, or not algebraic if I'm in a Kähler manifold, just curves if they are. Okay? Because when you have a curve, it defines always the current by this formula. You can integrate theta is 114. Okay? This is the current defined by the curve. Okay? Like here, it's the line at infinity. And very concretely, it tells you that this averaging converges to the same average, to the same guy with the line at infinity. Are there any questions? By the curves. It's like here, if I change, suppose I start with here, and I compose with a birational map. Then the line at infinity is going to be sent somewhere else. You might have an invariant curve. Maybe? Yeah. If the set of invariant curves, then the hypothesis is not satisfied. If it's empty, the hypothesis is not satisfied. And if it's empty, you are in CP2, then you have this theorem. And this current is not supported by invariant curve. It's a fat current. What this theorem with John Eric says, it says the following. Take a foliation of P2, where all leaves are dense. This exists, I know, there is a Russian guy who has constructed that. No, not Joanolu, no, leaves are not dense. But, okay, I forgot the name, sorry. But you can construct foliation in P2 where all leaves are dense, minimals. Then the current there is going to be supported everywhere, okay, because it's invariant under leaves. It's invariant. And it tells you that the averaging is going to distribute according to that, but according to a very special law, because this current might be dense, might have dense support, but be supported by something of small Hausdorff dimension. 3, not 4. This is completely unexplored. Other questions? So let me somehow sketch the idea of the proof. The proof, part of the proof, has nothing to do with foliation. It has to do with the theory of curves and with something that Dean and I call densities. You see, when you have an analytic set, say in C2 or a germ, you might have singular points, okay? And attached to the singular point is the multiplicity. And a way to look at the multiplicity is either through Lelon numbers, but the other way to look at it is just I'm going to take dilatation of the curve, multiply by lambda, and consider I'm in the projective space, and let lambda goes to infinity. What is the limit of these guys? It turns out it's a cone, and the degree of that cone is the multiplicity. If you replace a curve by a current, positive b degree 1, 1 for simplicity and closed, unfortunately, the limit doesn't exist. But the cohomologic class of the limit is unique, and it gives you the mass of the current. It gives you the density of the current near that point. How strong is the density? This is the case of a point. So it is very useful in dynamics to develop a theory when you replace the point by an analytic set, smooth, V. Okay? and you make dilatations in this direction, in the normal direction. So let me cheat a lot, because there are problems of complex structures, etc. Let me assume that the normal bundle is trivial, which is crazy, but I'm just trying to give you the idea. Then I take a current T, and I take the image by this. And they take the limits. The limits are going to be like tangent objects to my original object. It turns out that limits don't exist, but you can take cluster points. But the limits are objects, many currents S, and they are going to tell me when lambda goes to infinity whether the current T has mass concentrated near V, near the line at infinity or not. So, unfortunately, this is not enough for us. Because what do we want? V is the line at infinity. And we want to show that if we take T positive directed by the foliation, then T is just the line at infinity. So we can somehow subtract from T the mass it has on the line at infinity, and then we can assume that T has no mass on line at infinity. Then what do we want to prove? We want to prove that T is 0. Okay? Because if we prove T is 0, it means the only dD bar cross current is the line at infinity, and we have our convergence theorem. So you understand that we are after understanding the density of T near the line at infinity. Okay? So, in this case, actually, what I'm saying is correct, because it turns out that the complex structure of the normal bundle and the complex structure induced by P2 is just the same in this case. But in general, it's not, so it's technically much more difficult. But let's see, we are here. I take this guy, and what we prove is that the limit is P star nu, and that the mass of P is the normal bundle, and nu is what? Nu is, the mass of nu is the cohomology of T wedge the line at infinity. This means even T is just dD bar cross. This means that if we want to prove that nu is 0, if we prove that tangent currents are 0, okay, it would mean that nu is 0. It would mean the intersection of cohomology classes in P2 if it's 0, it means t is 0. Because we are in P2. Okay? And then the theorem would be proved. So the whole theorem is to prove that the limit currents, when you make the dilatations, are 0. I will speak it for 5 more minutes. Does somebody has, if I were not too obscure, maybe somebody has a question. So the proof is geometric in some sense. You want to prove t is 0. That's difficult. Then you look at the tangent currents. And you say, oh, this is a difficult theorem to prove that the tangent currents are of this type. Okay? And that nu is of this type. But if I can understand the tangent currents, then I'm done, because for cohomology reasons coming from P2. Okay? Or from this hypothesis on cohomology classes. Okay? So now we are back into foliations. Because this theory doesn't use foliation. This theory of density doesn't use foliation. Now we are back into foliations. We have a priori a candidate which we can write near the line at infinity in this way. These are the singular points. And now, when I'm away from singular points, I look at this A lambda t. H alpha lambda W equal alpha d mu lambda alpha. But it turns out that when you are in this flow box, this measure here comes from the measure you had on a smaller flow box by dilatation. Since the measure has no Dirac mass and the H alpha are bounded, you go to 0. You go to 0, that's simple. Hence, what I know is that the measure nu and then the current is a priori supported on the singular point. And on the singular point, they are hyperbolic. So I have a vector field that I can integrate. I don't know if the guys here who have worked on hyperbolic singularity realized that the leaves cluster on the separatrix, but if you remove the separatrices, they are closed. Closed. That's remarkable. And then the current T decompose on T alpha d mu alpha, and you have to analyze this T alpha. Now, basically, if I'm a wise man, and why not be wise at my age, I will not detail the computations. But I'm going to tell you what is the difficulty. The difficulty is you write T alpha. The difficulty is to understand the behavior of this positive harmonic function. And the only way you have to, the only information you have is that the mass of the current is bounded. So there are several tricks. First, to parameterize all the leaves by a sector, a fixed sector, and write things explicitly. And estimates show the alpha are Poisson integral of their boundary values and get estimates. The whole thing is about estimates. But the estimates are not too difficult to understand. The theorem with Foliations was very, very difficult estimate, pages of estimates. But here we have this new concept of densities that makes life much simpler. Okay? So what we, and the computation of harmonic integrals, etc., are reasonable, few pages, but not more than that. And you end up proving, extracting sequences, etc., but you end up proving that X is 0. And then you get this theorem. What's good about this theorem is that indeed we don't use much that we are in P2. We don't use automorphisms. That's very good. And probably there will be a version of the theorem with the Foliations in arbitrary surface. So it's to prove this theorem we had to introduce a new concept, which is in some sense the tangent to a foliation or the tangent to a curve. And then you use global geometry, because even this estimate I write here appear to be local. They are not. They are not. You use always that you are in a compact scalar manifold, because the estimates otherwise are just wrong. And then maybe I want to say one last thing. If you look at the literature, for example, of Lucy Arnett, when she works on foliations without singularities, but in the real category, she doesn't use currents. She uses rather harmonic measure, which correspond to currents when you take the trace of this current. So once I was giving a lecture in Dijon, and it took me a while to understand the objection I was having, I believe from Bonatti, because this was his objection, and it might be useful for others. But you take a sequence of currents, you see it converge. Why it doesn't converge to the point mass? And then everything you say is just bullshit. The point is that, and it's true that you can take smooth measures, probability measures, as nice as you wish, and you take weak convergence, and they converge to a Dirac mass. we are completely lost. So this is why it's useful to have the basics of currents. The beautiful thing is that the positivity this is like probability measure. When you have positivity by dimension 1, 1, that means it acts on forms of pi degree 1, 1, then this is just like, you have the same capacity like for measures. You can take limits, extracting subsequence. If you have dTn equals 0 or dd bar Tn equals 0, the limit satisfies also this equation. But then immediately, it cannot be a point mass, because the structure of currents tell you that if they cannot be concentrated on a coordinate chart in some way without being 0. Let me give you a proof. Suppose they have a current T, like here, dd bar T closed, and it's constant, it's supported on a ball of radius r. Okay? I claim it's 0. Which will be impossible because T, the mass is 1. Why is it 0? Because I take T applied to I dd bar mod z squared. This is the mass. This is the mass of the current. This is a Kähler form in C2 or Cn. See, if this is compact support, I put the dd bar here. Then this is 0, a contradiction. So, dd bar closed currents, when they are not 0, are very spread. They cannot stay even in Cn. It's automatic. It's part of the theory. Besides, they have very, very strong relation with geometry. They have multiplicity. They have. It's not. The way to look at them is this. You are in P2. You have algebraic varieties. Okay. You divide by the volume. Then you have currents of mass 1. You take limits. You get all positive closed currents. That's a deep theorem based on Hallmander estimates. This is how they are. But they are spread. They are horrible guys, but very rich structure. On the other hand, if you do dynamics of foliation, they are just unavoidable. Because what you do is you take an average and you take limits. If you don't have a theory of what are the possible limits, then you are shot. You know, it would be like doing, if you want to do ergodic theory and you don't want to know what measures are. Okay, so let me stop here.